Okay. So these two talks are really intended as an introduction to the role of the H principle in the theory of foliations. Homotopy theory of foliations is a part of the theory that is concerned more on the existence of foliations and their classification up to concordance, not the geometric or dynamical study of foliations, but really concentrating on the existence. And it turns out that the H principle is important in the same time as a spirit and as a provider of tools. We shall apply the Gromov's H principle on open manifolds for diff invariant open relations. We shall apply the theory of wrinkles. So I shall concentrate on, so everything will be, all the results almost will be very classical, but I shall give modern proofs of classical results. And a lot of things that I will explain, Yasha did mention of it quickly in the beginning of this summer school. So what is a foliation? Well, first of all, consider a manifold of dimension n, any dimension n divided in p plus q. For the moment, it may be closed open anything. And so consider a p-plane field. Some call it a distribution. Meaning that at every point of the manifold, you're given in the tangent space a vector subspace of dimension p. And it depends smoothly with the point. But in these talks, everything will be smooth, C infinite, except when otherwise stated. And we shall see that it is interesting sometimes to consider some CR differentiability class with R small. Anyway, so the definition is that C is integrable if in the neighborhood of every point you have a neighborhood with local coordinates in which the planes are parallel. So locally, you have a chart in which these guys appear as the planes parallel to RP in RP plus Q. So this is a foliation. Let's see examples and counterexamples. First example is that line fields are always integrable by the theory of ordinary differential equations. Unfortunately, as soon as so a counterexample, a non-example is x3 minus x2 to x1. Okay. The standard contact form, which is not integrable in the neighborhood of every point, or any point. And unfortunately, except for p equals 1, this is more like a generic case.
So you mean dx3?
Mm-hmm. Oh, yes. This is the contact form.
dx3?
Yes. And unfortunately, for every p between 2 and n-1, generic plane field, p-plane field is not integrable in a neighborhood of any point. So the question of the existence of foliations took very early the following form. Red says this in 1948. He asked the following the question, the fundamental question. Given p-plane field on a manifold, does it exist another one which is homotopic to the first one, and which is integrable? So this is the main question that we shall discuss. If you like, from a modern viewpoint, we can think of the space of integrable p-plane field on M in the space of all p-plane fields. We could think rather naively that this is a kind of formal foliation, a non-integrable p-plane field, and ask if this is a homotopy equivalence. All this is very naive. The answer is, so this is just the finite surjectivity. Well, this is far from being always true, and that is, but it turns out that it is true for p equals 2, but I think that it is the only case where reasonably we can hope that. And it's a big question for p equals, sorry, just for p equals 2 and q at least 2. So plane fields of dimension 2 in ambient dimension, in ambient manifolds of dimension at least 4. And it's a big question for p equals 2 and q equals 1, for two plane fields on three manifolds. Well, I won't really discuss this question, except maybe at the end, depending on time. I will concentrate on this so-called fundamental question, which is already a serious one. So, as a motivation, I would like to give first some very concrete results of the theory. to the fundamental question. Partial answers. Not always you, yes. Because the first really convincing things were Raoul Bott's works in 1968. Then there are the Goodbeyond invariants. Lots of obstructions, characteristic classes of obstructions, obstruction characteristic classes are known.
When you say that that's the first convincing result, do you mean that there were non-convincing proofs before, or?
Well, okay, Reb gave us something for Reb made notice that the relative form can be wrong in codimension 1 on through manifolds. Maybe I can answer this question. Yes, so in his thesis, Reb said the following. He shows that if so, it's for two plane fields or three manifolds. He showed that something which is very specific to codimension 1. If you have a leaf of the foliation which is a two-sphere, then all leaves are compact, and two spheres or maybe compact or maybe projective planes. So he said the following: if I take the ball, the three ball, minus a handle body of genus 2. So the complement had the right Euler characteristics so that you're sure that there is a non-singular vector field which is pointing outward through S2 and inward through the boundary of the handle body. And so the orthogonal is a plane field. Of course, you can arrange that it is integrable close to the two components of the boundary, just take the parallel surfaces. And certainly, this plane field, orthogonal to the vector field, is not homotopic to an integrable one relatively to the boundary, because there would be one leaf which is a sphere and one leaf which is sigma, and this is impossible. Codimension 1, this spherical sphere, I mean, the neighbor, the approximating leaves are also spheres, and but the limits also one, so you cannot have it. So this was the very first little counterexample to the fundamental question, but it is codimension 1, and in these talks I will not concentrate on codimension 1, rather on higher codimension. In fact, codimension 1 tends to be less flexible, more rigid than the other codimensions, and it is for the relative form. Well, you are given already a foliation on some subspace and you want to extend it. So not always, but Bott gave examples on closed manifolds of plane fields of, well, on CP. I think that the simplest example for Bott's obstructions are on CP5. There is a holomorphic hyperplane field that is regarded as a real plane field. It is of codimension 2, and it is not homotopic to any C2 C is of codimension, of real codimension 2, not homotopic to any C2 integrable. Sorry. Any integrable plane field. There is something about the differentiability class. So such an integrable plane field is said to also to be a foliation. Well, when one has an integrable plane field, one can consider the maximal submanifolds which are tangential and of the same dimension P. So this makes some partition of M into submanifolds of dimension P, which is locally like the parallels to RP plus Q. These are called the leaves, and this is called the foliation. And the foliation is said to be of class CR if the trivializing local coordinates are CR. Another way to say this is that a foliation is locally given by submersions, local submersions to RQ. And the class CR means that the submersions, the local submersions are of class CR. Then the plane field itself is of class CR-1, but it's not quite equivalent. There is a little something. So what here, not an integrable field, making a foliation tangent to a foliation of class C2. By contrast, the answer is yes for R equals 1, which is an important result of Topology. It means that any...
What is R?
Hmm?
R is the regularity.
Yes, it's the regularity. Any plane field is homotopic to 1, which defines a foliation of class C1. The local submersions are of class C1. And that's one of the main results of the theory whose proof has seemingly nothing to do with the H principle. So we could ask for a H principle proof. In particular, the reasons why there are obstructions beginning with class C2 have to do with the existence of curvature for some connections and these kind of things. So it looks strangely, very vaguely dual to the Nash-Kuiper things, things like that. Except that you're not trying to make immersions or embeddings of class C1, you're trying to make families of submersions of class C1. Maybe it's just analogy, maybe not.
Also, yes for R is 0, right?
Hmm?
Also, yes for R is 0.
Yes, also yes for arguments. Well,
Yeah.
Consequently.
Yes,
consequently.
easier.
The first Tsuboi's result, there is some analytical, dynamical things which are really non-obvious. But if you ask between C0 and C1 for Lipschitz, then there is it's It's a rather simple result for Lipschitz. Always yes for p equals 2. Turns out that for a two-plane field, there is never an obstruction to homotopy to a smooth integrable two-plane field.
So what does it mean to have a foliation, C0 foliation?
C0 foliation. Oh, it's a complicated concept. It's not the scope of well, this is one of the reasons why people developed very early in the 70s Lipschitz theory of foliation, because C0 is very bad. Lipschitz always yes. So this is first term. Always yes if Q equals 1, first term. And always yes if the normal bundle, consider the normal bundle to the foliation, that is 2m over c, if this bundle over m is trivializable.
Gail,
Hmm?
and 3, when you say yes for p equals 2, I thought it was an open question in dimension 3.
Sorry?
In 3, I thought you were saying that it's also open in dimension 3. Is it open in dimension 3?
No. It's classical in dimension 3.
It's just pi 0.
It's just
Yes, it's just by 0. So what is really open in dimension 3 is the pi 1 injectivity.
okay.
It is not known if you take two foliations on the three manifolds, which are homotopic as plane fields, if you can realize a homotopy by integrable plane field, that is. And there have been works by Hénard-Bontemps, Larcanché, before her, and they proved, Hénard-Bontemps proved that something subtle, if you take two foliations of the three manifolds, which are in the same homotopy class of plane fields, then they are in the same connected component of the space of foliations. But connected component in the sense of general topology, maybe not arcwise connected component. That the question remains open. It's very difficult. It's very difficult questions because it's difficult analytical questions. This is really not my scope here, but it amounts more or less to the following very difficult question. You consider the interval and the pairs of diffeomorphisms of the interval which commute. Is this connected? Is this arcwise connected? It's a very difficult question because the commutator of the diffeomorphism of the interval depends strongly on fine analytical things. Rank. So essentially, codimension 1 is more rigid, and especially in dimension 3, where you have very few room, it's a different subject. Okay, so I would like in these talks at least to prove this and that. And I will begin with this part, right? Because the proof requires some geometrical constructions, which are essential, but no preliminary theory. So I'm going to begin with one. So this was one introduction. So it's called, when this has, it's called the foliation theorem. In the parallelized case, let's prove it. So the theorem the normal bundle is realizable then C is homotopic to integrable smooth space. And actually, there are two cases, M open or M closed. And for M open, it was already done. What happens for M open? Well, such a C, this formal data amounts to say that Xi is the kernel of an epimorphism of tau M to R2, right? And so if M is open, as Daniel told us, by Gromov's diff invariant open relation H principle. This is the formal data for the submersion, and it is homotopic to the kernel of a genuine foliation. Of a genuine submersion. So it's done. Now for enclosed. For enclosed, as Harry told us, there is no such easy H principle for submersions on closed manifolds, but we can at least get from Xi a wrinkled submersion from F to RQ, and okay, whose kernel plane field is homotopic to the regularization. The regularization of the kernel plane field is homotopic to Xi. Well, from now on, I will not insist on verifying that the formal data are preserved. I will concentrate on making foliations, and always the formal data are verified. An exercise to verify that you stay in the right homotopy class of formal data. And so we have the solution, except that there are wrinkles. So what remains is to explain how given a wrinkle, you can somehow cancel it in the world of foliation, of course. That will not be given by a global submersion. We shall explain how to cancel wrinkles by changing them to foliation. In cancel wrinkle in the world of foliation. So it's purely geometrical constructions, and I will make some preliminaries. On filling the holes for 4-dimension foliations on 3 manifolds. So what do we mean by a hole in general? And this was the first constructions of this kind, which later have been, there have been analogous constructions on for contact structures and things like that. So in the beginning, one would consider holes for foliations. That means that you have to make a foliation in some manifold, and you could, in general, using the H principle on open manifolds, you could make it except in some zones which remain to be foliated. So you already have a foliation close to the boundary. And you want to extend it inside. That is what we call a hole. So here we consider, I want to give the key for some standard holes that one meets naturally. So what one may call the straight standard hole. Everything is in dimension 3. For 2 plane fields. So it's D2 cross I. And D2 cross 0 will be a leaf. This leaf, D2 cross 1 also. So these parts of the boundary are tangential to the foliation which you already have built in the complement. And on the contrary, the vertical boundary will be transverse, and even the verticals in the vertical boundary will be transverse to the foliation, so that the trace of the existing foliation on this boundary is this. Is the foliation of the annulus of dimension 1. And it is essentially the same as considering diffeomorphism of the interval. The diffeomorphism is the first return map onto the fiber above the base point in this one. And reciprocally, given such a diffeomorphism, you can suspend it to a little foliation like that. And so this is our data. And
So can you say again what all the lines mean? What are the lines on the top and the bottom of the cylinder?
sorry,
The hatching on the top of the cylinder, what is that?
it's a diff. It's here the foliation is tangential.
Okay.
And also phi will be with compact support in the interior of the interval. Such details I will not insist, but it will be okay.
So like only the spiraling lines on the side of the cylinder, those are like somehow where the foliation leaves intersect transversely with the.
Yes,
Okay.
exactly. Yeah. So outside you have foliation like this. And so the bad news, so filling this hole is extending the foliation inside. And the bad news is that it is fillable only in the stupid case of phi is the identity. Of course, if phi is the identity, you can fill it by disks. We don't have disks, and this is the only case. And the reason is Rabe's global stability theorem, the one that I had said before. Usually it's given on closed manifolds, and you assume that there is one leaf which is a two-sphere. But you have the like in this relative case, the fact that one leaf there is a disk implies that all the leaves are disks and inside. And of course, this is incompatible with phi being not the identity, because if phi is not the identity, it has an infinite orbit because it is orientation preserving. And so you have an infinite spiral, which cannot be the boundary of a compactive capsule. So one observation of Thurston was that things become completely different if you round the hole, that is, if you change the interval to a circle. So the round standard hole, now it will be S1 plus D2 plus S1. The vertical axis here is S1. And you're given the suspension of the diffeomorphism of the circle, no, not the interval, say orientation preserving, and this is always fillable. Just explain why. We first consider the case of what we call a linear foliation of the bonding to torus. That is phi is a rotation of the circle. In that case, so I will on the boundary to torus, this foliation by lines is the suspension of phi. Then S phi it has a constant slope A, So it's given by the one form, dz, the coordinate in S1, minus a d theta. I put polar coordinates r theta in the horizontal plane. And the miracle is that this little one form is closed. And so there is a very easy formula. So you consider the solid torus minus a smaller solid torus. That is the domain R between 1/2 and 1. You can give a formula that will give an integrable one form, namely 1 minus u over r dr minus or plus u of r alpha, is that correct? Where u will be the plateau function, cutoff function, equal 1/2, yeah? Yes. Yes. So this form, omega, is satisfies Frobenius equality d omega which omega equals 0. So it is integrable, it is non-singular. And here is a drawing of the foliation that you obtain in this space between the two solid tori. You obtain this. Here are the is my sign correct here? I think yes. It's rounding like this, and they accumulate on this smaller two torus, which is on this interior two torus, and you just complete by what one calls a rate component, which fills the interior two torus. The rate component is a simple object which is extremely important in all the constructions of foliations. It's on D2 cross S1, a foliation which is tangential to the boundary. The two torus is a leaf, and the interior leaves are homeomorphic to the plane. And they turn and turn and turn around it infinitely many times and accumulating on the boundary. And it's invariant by the action of this one. Right? And you always choose that the foliation is infinitely flat on the boundary, so that when you make such a gluing, it is infinite. So this is the case, the special case of the monodromy of the whole is a closed one form. And the general case where phi is any diffeomorphism of the circle is also true but much more difficult in the sense that it relies on Hermann's analytical theory of the diffeomorphism of the circle. Michel Hermann proved the following. Every orientation preserving diffeomorphism of the circle is a product of a rotation by a conjugate of a rotation. So there is a lot of analysis there. And so this gives the recipe to fill the suspension of any diffeomorphism of the circle. Maybe we could have a first figure.
Can I put the lens? So the figure is here, but I can just also share with the yeah, maybe we'll just okay.
Thank you. It will be short. You recognize. So here are the suspensions of the two rotation rho and rho prime, which have been filled accordingly to this recipe. And you just kind of glue them by this little bridge using the monodromy psi to glue the two around a small neighborhood of a fiber in the boundaries. And then obviously when you make a turn around the boundary of the union, you apply rho prime followed by psi minus 1, followed by rho, followed by psi. Or maybe I'm not completely right in the signs, but the global monodromy, the thing that the first written map on a vertical when you do a complete turn is just this. Thank you. This is simple but brilliant idea. That's done in the early 70s. And then they would like, in order to complete for the proofs of the foliation theorem in the parallelizable case, to discuss a parametric case of that one. But to simplify, let's take a rotation. Let's consider rotations, but make the angle of the rotation vary. So from 0 to 1. So for t equals 0, of course, I can fill the stupid foliation of the two torus by circles by horizontal disks. And I make one parameter, a continuous one parametric family of inside foliations which follow and fill this deformation of the foliation on the boundary. The answer is no. For a very simple reason. Imagine the foliations close to this one and filling that one. And since the leaves are close to this one, their tangent spaces are transverse to the verticals inside. So they cover the base. And the base is disk, it's simply connected. So every leaf would have to be itself a disk. And so if t is non-rational to 2 pi, then these leaves are infinite, not compact, and of course they cannot be boundaries of the disk. So that's a bad news. However, Watson made an observation that if you modify a little, we should change a little the data, you can solve the problem. Sometimes I call it Thurston's flexibility trick. The same data, except that I make the family of foliations on the boundary stationary for some small time epsilon. So up to time epsilon, it is still the horizontal foliation on the boundary by circles, and then it begins at time epsilon, say, it begins to the slopes begin to vary. Then we can do the following. So for t equals 0, we take the opportunity of this time where the data on the boundary does not change to change the foliation inside. So here it is disks. We make bumps in the disks. All the disks inside. And when we arrive at time epsilon, if we make the bumps correctly, then we can achieve the following transformation. There is a kind of qualitative change of the foliation, although the plane fields vary in a smooth way. Suddenly there appears the leaves become like this, because the bumps have gone to infinity turning in the circle. And inside you would have a red component. This is easy, it is easy to give a formula. And then once you are in this situation with the red component inside, it has become flexible, and you can do the same as here and make so the red component remains fixed inside, and around it you can easily it's easy to give a formula. You can easily make the slopes vary. There is something crucial. The web components for foliations are a little like over-twisted disks for contact structures, or these for loose things. They introduce some flexibility.
Can you maybe repeat what made this work? That I had some epsilon time to make this performance move inside?
Yeah. And at time epsilon, it has become this foliation, which is the same as that one, except that the slope is 0. And the leaves are just annualized that go up.
The set of T where I have a disk in the middle, will it be open or closed?
It is open.
Okay.
It for T's less than epsilon. That time epsilon, it has become. Stop. Okay.
So,
So these were the preliminaries on.
so I can't deform this not fillable thing. It's not deformable to this fillable thing, right? Because of some micro flexibility. If I could deform, I can't like take the top case and just slightly deform it to make this epsilon time be there.
Sorry, I haven't understood.
I'm saying it's not like I can take the top board where it's not fillable and just say I'm going to just like slightly wiggle things and get myself to the second situation.
You can reprompt this time, right?
Yeah.
If you allow yourself that.
Can I? Okay.
Well, it depends what the rules of the game are.
Oh.
I mean,
This certainly has some relation, some small relation with what you told us, Alexander, because there is under this there is a situation of quasi-vibration for the restrictions of foliation to the boundary. In fact, I think that I can prove that the global result for two-dimensional foliations, at least in higher dimension, well, that the restriction maps are quasi-vibrations. Okay, so with these little exercises in mind, we can begin thinking of changing any wrinkle to a foliation. We begin with the codimension 1 and with the dimension 3. Well, codimension 1 and codimension 1 and larger dimensions are actually difficult. I will say a word about it, and I won't do the proof in that cases, which are not necessary for the higher codimensions anyway. So we are given a wrinkle on a 3-manifold. It may be open, or anyway, everything will happen in a small neighborhood of the wrinkle. Recall, as Kai told us, that in codimension 1, a wrinkle is simply two singularities, two critical points of a function, of a Morse function with a gradient-like vector field, an orbit of a gradient-like vector field between them. The C prime above and C below. And I think to the case where C prime is of index 2, and where C is of index 1. If it is 1 and 0 or 3 and 2, then it is easier. But wait, this is the series. Okay, so I claim that this can be changed to a whole. I can cancel. So first of all, in general, what this data is not enough to change this to a foliation in an arbitrarily small neighborhood, in the sense of creating a foliation which, on the neighborhood of this, close to the boundary of this small neighborhood, would coincide with the one given by the function f. But we can do it if we allow ourselves to create some hole. And even some holes, I pretend that we can do the job, provided that we create 4 standard straight holes, which will belong and parallel to the gradient line.
Right, 4.
Why 4?
Yeah.
We'll see. 4 because it's the cardinal of S not cross S not. So yeah, it's a good question. It will be crucial that it is the cardinal of S not cross S not. Okay, so first of all, let's try to remember the cancellation of singularities of critical points. The classical cancellation of critical points is the most function. Well, and usually in books, it's not so well made. I mean, even in the best books by the best authors, because something which remains strange, not really clear, is the place where you have to change the function in order to modify, in order to cancel the 2 critical points. And you can make the exercise or look at some published proofs that you can, these data are sufficient and answer the question. Assume, so I'm thinking to a pseudo gradient, gradient-like vector field, and my gradients are always descending. So I'm thinking to all these gradient lines descending from C prime, and say that I stop them at some level f equals any value between f of C and f of C prime, any value v. And I'm thinking also to the stable manifold of C. Which I stop at the same level. And the lemma is assume that this can be done. That is, all the gradient lines from C prime go to the level V, which is not obvious, especially if M is open. And assume that all the gradient lines converging to C also come from the level V. And assume that in the level f equals V, the 2 boundary spheres meet transversely in one point. Then says the lemma, you can cancel the two critical points by changing f in an arbitrarily small neighborhood of this union of two disks. The two disks, I call them D prime upstairs and D downstairs. And okay, you can make the exercise, which is not so easy. I haven't completed the version. So this will be essential. May we have the following figure.
So I have more, right? I guess.
Ah, yeah. Of course.
For example, if you prove the H convergence there, would have this condition satisfied, right? In the usual proof, the H convergence there.
Yeah. May did not really completely think in those terms. He thought really in terms of handles. And most authors, for example, Milner, think in terms of elementary cobordism. And so this is not. So here is the figure. So maybe I should have said that in the beginning, we don't have this cancellation disks, but at least we can consider a small disk upstairs, which is the gradient line from C prime stopped after a time epsilon, and the like downstairs. Now I have this gradient line. I consider the portion of the gradient line from the boundary of the upper disk, D prime, to the boundary of the lower disk, D. And I zoom on this situation. So this is the gradient line. Here it hits the boundary of the lower disk. The lower disk is there, with a singularity there. And upstairs also. In Z prime, the gradient line quits, descending gradient line quits the upper disk. And let us, so for the moment in the beginning, the foliation in this area is horizontal. It's just the level sets of F. So let us just decide where the holes will be. The holes will be 4 pillars like this. We should think of the orthogonal directions of the boundaries of the two disks. And if they, one is there, the other is there. So think to this square and to the 4 corners of the square. And the height of the pillars is such that the bottom of the pillars is a little lower than the boundary of the lower disk, and the top of the pillars is a little higher than the lower boundary of the upper disk. And just forget the foliation inside those 4 pillars. So it makes holes. And thanks to these holes, one will be able to make modification of the foliation, which is shown on the next view. Okay, thank you. Here it is. So say that between 2 of the pillars, you have a gate. and think to a small. Oh, it's okay. Thank you. Think to a small neighborhood of this gate. Choose a diffeomorphism of the interval which sends the point Z on the upper boundary of the lower disk to the point Z prime in the lower boundary of the upper disk, and make a very simple transformation, which is between those two pillars. You put, instead of the horizontal foliation, you put that one, which realizes the diffeomorphism phi of the height. I can do this since I have forgotten the foliation inside the pillars. And the like on the other side with the mirror symmetric image between the two other pillars. So what happened then? With the simple modification of the foliation, the lower, for the new foliation, the upper boundary of the lower disk now lifts up and goes to touch the upper boundary of the lower boundary of the upper disk in Z prime. Note that the upper disk is not changed at all. Very simple. And then in the union of the two disks, I can modify the function f to another function which is without critical poles. So in some way, the lower disk pushes a pseudopod that goes to touch the boundary of the upper disk. And this makes the cancellation possible. Thank you. A question? Till what time is it finished?
Depends on you, but maybe.
Yes, because I need at least 5 minutes or 10 maybe to finish this case. So we may resume on next time. For the moment, we have changed the critical points to, so we had a foliation with more singularities, and we have changed the more singularities to holes, which we shall see next time. To holes which are not fillable, as was explained. And we shall see on next time that it is, however, possible to do it. And this will be the key for higher codimensional and cancellation of all wrinkles. Thank you.
Question?